Hello students, welcome back to the course on Principles and Chemical Applications of Thermodynamics. And today we are going to talk about the first law of thermodynamics and the associated concepts of internal energy, heat and work in a quantitative fashion. So first of all, before I state the first law of thermodynamics, I would like to introduce to you the extensive and intensive state function. We have already discussed that the equilibrium state in thermodynamics is described in terms of certain properties of the system, and these are called state functions because they specify which state the system resides in. Now, of all the properties that we call as state functions, there are two types of properties which we find useful. The first is known as the extensive function. So, what is an extensive state function? An extensive state function is a property of the equilibrium state of the system that depends on the amount of substance present in the system. An useful example is the volume of the system. On the other hand, when we talk about the other type of state function, which is intensive, we are talking about a property of the system that does not depend on the amount of substance present in the system. And the two quantities that we have already talked about which fit this definition are temperature and pressure. Now, with these definitions already introduced to you, now let me go back and give you the statement of the first law of thermodynamics. So, the first law of thermodynamics says that there is an extensive state function which is given this symbol U such that for any closed system undergoing a change in state, the corresponding change in U is given by delta U is equal to Q plus W. So, this is the statement of the first law of thermodynamics. You might wonder, where did this law come from? Of course, this law was formulated by carrying out a thorough investigation and analysis on a wide range of experimental data, and the observations were consolidated into a single statement that has been presented here. In this statement, I have three quantities involved. So, let me talk about what these quantities are. First, I have U, what is known as the internal energy. Then I have Q. Q is heat, or the form of energy that we supply to a system when we heat it up, or the form of energy that we take away from the system if I keep the system in diathermal contact with a very low temperature bath or reservoir. Now, what is work? Work is that form of energy where I am not really heating or cooling down the system, but doing, for instance, some kind of pressure volume changes. That is, I am changing the volume of the system by applying some pressure. And therefore, the first law of thermodynamics tells you that if I have a closed system, there are two ways in which you can change the internal energy U. One, by allowing the system to exchange heat with the surrounding, and second, by allowing the system to be worked upon, or by by allowing the system to do some work on the surrounding. Now here, when you talk about these individual quantities Q, W, etc., you must realize that these are algebraic quantities. And there is what is known as a sign convention usually adopted to describe whether it is a positive quantity or it is a negative quantity. In the discussion following the convention used in the textbook that I have referred to, I am going to use this sign convention. Any form of energy which is going to contribute to a positive change in U, that will be associated with a positive sign. Therefore, when I have a transfer of heat to the system from the surrounding, I am increasing the internal energy of the system, which means during this process, delta U is going to be greater than 0. So I adopt the sign convention that when Q refers to the amount of heat transferred to the system from the surrounding, Q is greater than 0. Obviously, when I am transferring heat from the system to the surrounding, then the system is losing a part of its internal energy in the form of heat, which means that under such circumstances, delta U is going to be negative. Therefore, I would say that under such circumstances, I will assume that Q is less than 0. Let us next consider the two situations where work is being done by the system or work is done on the system. So if I consider expansion of a system against a constant external pressure, in that case, the system is doing some work on the surrounding at the expense of its own internal energy. Therefore, I would say that under such condition, delta U is going to be negative. As a result, I would adopt this sign convention that W is negative. Now, if it so happens that I compress the system by applying an external pressure on it, then I am doing work on the system. So, the energy that is involved in the work is being transferred to the system. So, during the change in state, the internal energy is going to increase, and correspondingly, I will say that the work W is greater than 0. With this sign convention in mind, let us next go and check for what happens to delta U in different types of changes in state. First, if I have an infinitesimal change in state, then instead of delta U, which is the change of internal energy during a finite change in state, I have the differential of U, du, that is the infinitesimal change associated with the infinitesimal change in state, and du is now going to be dq plus dw. As you note here, this is an exact differential, and these two quantities, as I have discussed in my previous lecture, are inexact differentials. Now, if I have an isolated system, I know that in an isolated system, the system is surrounded by a rigid, adiabatic, impermeable wall. Since the wall is adiabatic, there will be no exchange of energy in the form of heat between the system and the surrounding, and therefore under such condition dq is equal to 0. Since the wall of the system is rigid, therefore there will be no work done by the surrounding on the system, or the system will not be performing any work on the surrounding involving any change in volume against a pressure. As a result, I would say that dW is also equal to 0. Now, if I put back this condition into the first law in its differential form, what do I get? I must be getting du equal to 0. Therefore, in an isolated system, you are finding that du is equal to 0, which means that u for an isolated system is a constant. And this is the reason why I have said that at equilibrium, the isolated system state can be defined by assigning a given value of u, a given value of volume, and a given number of particles contained in it. Now, if I have only an adiabatic process, in that case, dq is still equal to 0. But now one of the walls is fitted with a frictionless movable piston, and by moving this piston, you can actually transfer work into the system, which means that now during the change in state, du would be equal to dw. And as you can see, if I am doing work on the system, dw is positive, and therefore du is positive, which means that the internal energy of the system will go on increasing. Now, if I have a cyclic process, once again, then for a finite cyclic process, delta u, this is a cyclic integral over du that must be equal to 0. Why is that so? Because in a cyclic process, delta u, that is equal to u final minus u initial. And since in a cyclic process, u final is equal to u initial, I must be having delta u is equal to 0. And this would then mean that q plus w along this cycle must be equal to 0. Moving further, now let me think of a typical experiment in which you are carrying out a change in state, and I am considering a closed system. So, in this particular example, I have chosen to work with a special type of closed system, which is an isolated system. So, my initial equilibrium state is characterized by some gas contained within a cylinder or a box having volume V, and there are capital N number of particles of gas present in it, and have surrounded this cylinder by an adiabatic wall. Now, I am going to induce a change in state of this system. So, what do I do for that? I convert one of the walls here as follows. I convert it into a diathermal wall, and then for some time I heat the system. So, of course, you understand that from the surrounding, some heat will flow into the system in this direction through the diathermal wall, and then after some time, if I switch off the source of heat and remove the diathermal wall, what will happen is the system will now have some excess energy, but still it is an isolated system because it is again surrounded by an adiabatic, rigid, impermeable wall. But if I allow the system to equilibrate, then what would be the difference between the initial equilibrium state and the final equilibrium state? I would understand that once again, the final equilibrium state will be characterized by some given value of energy, U2, but the volume and the number of particles would have remained the same. because of the way I have affected this change in state. So in this example, I understand that the initial equilibrium state and the final equilibrium state, they differ by the values of internal energy that they have. So in this example, since I have added energy in the form of heat to the system, I would say U2 must be greater than U1. I could have put in an additional amount of energy to the system in a different way. How that could have been done? And if I carried out a change in state by attaching a piston on one of these walls and push this piston down in this direction, then I would be supplying energy to the system in the form of pressure volume work. Now, what would happen to the system? If I apply this external force on the gas for some time and hold the piston there and allow the system to equilibrate, this would be the final equilibrium state of the gas. Now, as you see that in the final equilibrium state, the volume of the gas has decreased because I have compressed it during the change in state. Now, here I have the final volume of the gas something different from the initial volume of the gas. Okay? And not only that, I do expect that since I have done some work on the system, therefore, compared to the initial equilibrium state, in the final equilibrium state as well, I will have this new value of internal energy. So the first law of thermodynamics tells you that if I have a closed system where the number of particles are not changing, in that case, I can always change the value of internal energy either by supplying heat or by performing some work on the system. And the result would be there will be a change in the internal energy from the initial equilibrium state to the final equilibrium state. Now, if I go and look for the different types of thermodynamic processes that are possible when a closed system passes from an initial equilibrium state to a final equilibrium state, I can think of processes like an isothermal process. So, as the name suggests, that this process will be carried out at a constant temperature. Iso means equal and thermal corresponds to temperature. Similarly, I can have isobaric processes, and these are constant pressure processes. I can have isochoric processes or constant volume processes. Then I can have adiabatic processes where there is no heat transfer, and I can have cyclic processes as well as reversible and irreversible processes. Now, let me go ahead and ask this question. How do we carry out such processes? So, let me go back and take this example of once again a cylinder of gas which is surrounded by a rigid wall on three sides, on this side, as well as this side, and the lower part of this vessel, this can either be adiabatic or diathermal, which means depending on how I am designing the experiment, I can have the lower wall of this system either adiabatic or heat conducting, heat non-conducting, or diathermal or heat conducting. On the top wall, I have put a piston here, and on the top of the piston, I can put in different masses, and by that I can adjust the pressure that is being put on the gas content in my system. Now, how shall I carry out an isochoric process? You see that there is another mechanism over here, which is a locking pin. Now, if I put this pin in this slot, then what happens is the piston cannot move. If the piston cannot move, in that case, I will have the volume of the gas remaining constant all throughout the process that I am going to carry out. Then, if I want to heat the system, I will make this bottom non-insulated or diathermal and supply some heat through this wall. Then I will be having isochoric heating of the gas. Now, if I want to carry out an isothermal process, what shall I do? Once again, I will do the following. I am going to ensure that my system is kept at isothermal condition. So, how do I do that? The way to do it would be as follows. Once again, I will have this thin bottom and this lower wall will be diathermal in nature. I will keep my system in contact with some kind of a thermostat, which may be a hot water thermostat or an ice bath, depending on the temperature at which you are going to work on this system. And then I will take this locking pin off. Now you have ensured that the volume can change. So in my experiment, I will allow the system to equilibrate such that initially the temperature has acquired, the gas has acquired the temperature of the thermostat by exchanging energy through the lower wall, and then I withdraw the pin. Then depending on whether the pressure is applied from outside is less or whether the pressure applied by the gas is less, there will be an expansion of the gas or a compression of the gas. So in that case, the change in state that I am talking about is an isothermal expansion or compression of the gas. Similarly, if I want to talk about an adiabatic process, in that case, how should I prepare the initial equilibrium state? I am going to prepare the initial equilibrium state as follows. I am going to make the lower wall adiabatic now, so that there is no heat exchange through the lower wall, and then I can have the pin here. So this entire system is now insulated. So this is my initial equilibrium state. Now I withdraw this pin. What will happen? Depending on the pressure of the gas and the masses that I have put in here, the gas will either expand or compress. Therefore, I will be carrying out an adiabatic expansion or an adiabatic compression. Now, if I want to quantitatively indicate exactly how these processes are changing the measurable properties of the system, like the pressure, volume and temperature, we do so in terms of what is known as a PV indicator diagram. So let us choose the system of 1 mole of an ideal gas, for which we know that there is an equation of state which connects these quantities like pressure, volume and temperature through the ideal gas equation of state. Okay. So, my question is, how do I represent the thermodynamic processes when 1 mole of an ideal gas is present in a closed vessel, and I am going to do so in terms of a PV indicator diagram. Actually, I should be talking about a PVT indicator diagram. So, this is how the PVT indicator diagram look like. So, what I have done is I have simply written P is equal to RT by V. So, I am going to vary volume, I am going to vary temperature, then I can find out what the corresponding value of P is using the ideal gas equation. So, if I now plot the corresponding value of pressure along the third direction, what I have is a three-dimensional surface which has been colored by light blue in this picture. Now, if I want to think of an isothermal process that is taking place in my system of 1 mole of an ideal gas, so I will be visualizing the isothermal process like this in my system, where this is my initial equilibrium state. Then it goes through a series of states to a final equilibrium state. And along this path, this line, I have the temperature remaining constant. Actually, you have seen these pictures much more frequently in terms of what is known as a pressure volume isotherm. So, isotherm means the temperature is constant. And here you see that at different constant temperatures, I have different isotherms. And therefore, this is the typical PV indicator diagram, where you can follow the passage of the system from one equilibrium state to the other at a given temperature. Now, if I have an isobaric process, which means a process at constant pressure, so in this light blue surface, that is what would correspond to an initial equilibrium state and a final equilibrium state taking place when the pressure is kept constant. And this is typically the indicator diagram that you see, where you are varying the volume, you are varying the temperature at different constant values of pressure. Similarly, you can have isochoric processes being represented here, where the system passes from one initial equilibrium state to another equilibrium state. So, when the system passes from this equilibrium state to this one, I actually have the pressure versus temperature curve at different values of constant volume. So, similarly, we can have adiabatic processes and cyclic processes. So, what we have learned in this lecture is how to change the state of a system in a given thermodynamic in a condition. So, we have seen that there may be many different possible ways in which you can carry out a change in state. And when there is a change in state, you do see that there will be an associated change, for instance, in the internal energy of the system. And this internal energy will be changed through two channels. Number one, it can be changed by heating or cooling the system, or it can be changed by using some work that will be done on the system or by the system. And this change in state can be visualized in terms of some pressure volume or pressure temperature or temperature pressure indicator diagrams. In my next lecture, I will talk about a very important concept of reversible and irreversible changes in state and how to use the PV indicator diagrams to represent them. Thank you.